Hello, my name is Natalia Valderrama, and today I will present our paper titled Towards Holistic Surgical Scene Understanding. This work was developed in Sinfonía, the Center for Research and Formation in Artificial Intelligence from Universidad de los Andes, in collaboration with Fundación Santa Fe de Bogotá, both located in Bogotá, Colombia. Our work develops in the context of robot-assisted surgery as a minimally invasive alternative to traditional open surgery and their potential complications. In particular, the Da Vinci surgical system allows the surgeons to control the instruments easily and increase the precision and overall the instrument's motion, giving rise to augmented surgical abilities. However, receiving feedback or automated guidance from these systems still is a limitation and an open-ended research topic. The development of assistance with active surgical intervention is an ongoing research that integrates the primary areas of medical imaging and computer-assisted interventions. At the core of this research lies the endoscopic vision community and the interest of comprehending and modeling robot-assisted surgery. To achieve this goal, our community has studied fundamental aspects of the surgical scenario, first enabling the systems to understand the anatomy by performing tasks such as segmentation and classification of the organs, tracking and relocalization of specific structures, and 3D reconstruction of the anatomy. Additionally, allowing the methods to understand the general and the specific surgical workflow of multiple procedures by instrument-related tasks and non-specific action detection, the latter by surgical phases and steps recognition. More precisely, benchmarks and conference challenges have been developed in the area of surgical workflow, focusing on just individual tasks or else subset of tasks. Our work stems from the observation that the current state does not exploit the intrinsic complementarity of these tasks. This observation motivates the study of relationship between well-established tasks as an initial step towards holistic analysis of surgical procedures. It follows that the spatiotemporal relationship between the multi-level activities and instruments is essential for holistic understanding of the scene dynamics. We then consider that a phase can be decomposed into multiple steps in which surgeons use specific tools to perform fundamental actions. Studying the hierarchical decomposition of the scene along with the interactions between the elements leads to a holistic surgical scene understanding. This concept of holistic analysis includes the recognition of surgical phases and steps which divide the whole surgery into parts and determine, respectively, primary and secondary milestones during a procedure. Also, in shorter periods, our proposal includes tool detection and the recognition of their atomic actions. This last task goes back to the concept introduced by Barker and Wright in 1954 regarding the fundamental units of human actions, which in turn inspired the development of the atomic visual actions dataset. As defined in AVA, atomic actions have two main principles, generality and atomicity, implying they do not depend on a specific scenario or nor they can be further decomposed. We extended this concept to surgical scenes. Hand in hand with the Fundación Santa Fe de Bogotá and the robot-assisted surgery program, we collected radical prostatectomy surgeries videos performed with the Da Vinci surgical system to enable the creation of PSI-AVA, the Phases, Steps, Instrument, and Atomic Visual Action Recognition dataset. Our dataset contains 8 video instances with approximately 20 hours of data and annotations for 11 phases and 21 steps. 2,224 keyframes were annotated, resulting in 5,804 bounding boxes with 1 of 7 instrument types and up to 3 of 16 atomic action classes. We made a comparison between our dataset and current surgical workflow analysis datasets, and different to these previous works, PSI-AVA provides enough information to study whole surgical scenes instead of focusing on a single independent task. With PSI-AVA, we propose a benchmark with multi-level annotations to explore into 4 tasks, in which some of them have hierarchical relations. Also, we propose a 2-fold cross-validation setup, each one composed of 4 video instances. For the performance evaluation, we established the mean average precision at 0.5 intersection over union as a metric for the short-term task and the mean average precision for the long-term task. Along with our dataset, we developed one method to individually solve each task in PSI-AVA. TAPIR, a transformer model for action, phase, instrument, and step recognition in surgical videos. Our method's input is a video sequence that is analyzed with a video feature structure, and then a classification head makes the prediction on the mainframe of the sequence. We use multi-scale vision transformers as our video feature structure. MBIT embeds patches of a video sequence and uses the transformer blocks to produce a classification token and spatiotemporal comprised features. These features are the inputs for a classification head, which changes depending on the task. To predict the phase or step, the classification token performs long-term recognition thanks to a linear layer. And regarding the instrument anatomic action predictions, we perform the instrument detection with a detection architecture. In particular, we train deformable DTR, a transformer-based method, to detect the instruments in PSI-AVA. And then we use the proposed bounding boxes and the computed features to complement the spatiotemporal features in the box classification head. A classification layers make the final prediction. We compared the performance of a slow-fast at TAPIR with a video swing transformer instead of MBIT and our final method TAPIR. TAPIR outperforms the slow-fast by almost 10% and 12% in mean average precision for phases and steps recognition tasks, showing more temporal consistency. Here, TAPIR improves almost 5% mean AP at 0.5 IOU in our challenging atomic action recognition task. The figure shows how both methods fail to recognize the atomic actions, showing its difficulty. However, TAPIR is able to keep coherence between the possible actions, contrary to slow-fast, which simultaneously predicts opposite actions, for example, travel and steal. We validated PSI-AVA based on the behavior of the proposed baselines in our dataset and in public databases whose task definition is equivalent to us. To compare the phase and recognition steps, we used the MICCAI dataset, and here we observed that the performance of TAPIR overcomes the slow-fast in both tasks and both datasets. Also, to validate the instrument detection task, we modified the ENDOVIS 2017 dataset instance segmentation annotations to bounding boxes. And here again we see an increase in the performance with our method, and this consistent improvement provides empirical support of the adequacy of PSI-AVA for holistic surgical understanding. In this set of experiments, we studied the complementarity between the task of detection and classification, specifically in the instrument detection and atomic recognition. Without instrument-specific features, TAPIR classification head loses the spatially localized information, and adding instrument-specific feature improves the performance of both instrument detection and atomic action recognition tasks. To conclude, our work presents a novel benchmark for understanding surgeries in a holistic, multi-level manner, introducing and validating PSI-AVA, which enables the intrinsic relationships between its tasks. Furthermore, we propose TAPIR, a transformer-based baseline method able to solve each of the tasks in PSI-AVA. Currently, the effort of our community to analyze the surgical workflow has been essential on the way to comprehending and modeling robot-assisted surgery. We hope our work complements it and serves as a motivation for future work to steer towards holistic surgery scene understanding.